All right, welcome to the Explainer. Today, we're going to talk about something huge, a really fundamental shift in how we build software. We're talking about a change that might just redefine the future of code as we know it. For as long as anyone can remember, building software has been this constant balancing act. It's like you're forced into this impossible choice. Do you want it to be fast? Do you want it to be safe? Or do you want it to be simple to write? The running joke is you can pick two, but good luck getting all three. Okay, let's make this real. Think about the classic showdown, right? On one side, you've got Python. It's super easy to get started with, really flexible, but let's be honest, it can be kind of slow. And on the other side, you have C++. This thing is a beast, unbelievably fast, super powerful, but it's tough to learn, and it's notoriously easy to make these little memory mistakes that turn into massive security holes. So to deal with all this complexity and, make sure our software could run pretty much anywhere, we came up with what seemed like a pretty smart idea. We decided to just add more layers. Think of it like putting a blanket on top of another blanket. All right, let's break down how this layering thing actually works. The first big idea was the virtual machine, or VM. The idea was simple. Just wrap up your entire application inside its own complete operating system. Now, that gives you amazing isolation, for sure, but it's also super heavy. You've got all this duplicated stuff, which means a whole lot of wasted resources and overhead. So VMs were kind of clunky. That's when containers came along, and they were a total game changer. They were so much lighter. Why? Well, because all the containers running on a single machine could share the main operating system's core, the kernel. That meant they started up way faster and used a lot less memory. But even with containers, we're still adding new layers, new dependencies that someone has to worry about. And this whole idea of layering, it really reached its peak with these enormous cloud platforms. Think of something like OpenStack. It's this incredibly powerful system, mostly written in Python, that basically wrangles all this complexity for you. It's a full-blown infrastructure as a service, a virtual data center at your fingertips. But here's the catch. Look at all these different parts. While it's super powerful to have everything broken down into modules like this, you end up with this gigantic, tangled web of services. And every single one of them needs to be set up, locked down, and kept running. It's like, in trying to solve one problem, we just created a whole new one, a monster of complexity. Okay, so what if we've been looking at this all wrong? What if we could actually go back and break that original impossible trade-off? The whole speed versus safety versus simplicity thing. Well, a whole new wave of tech is trying to do exactly that, and it all starts at the very foundation, the programming language itself. Enter Rust. And the results? They're just staggering. Look at this. When Google started using Rust in the Android operating system, they saw the number of memory safety bugs, those nasty security flaws, drop by a factor of 1,000 compared to the old C and C++ code. No, that's not a typo. 1,000 times better. And hey, it's not just about locking things down. The code is just plain better. The stability is incredible. We're talking about changes made in Rust being 4 times less likely to get rolled back because they broke something. Think about what that means for developers. It means the code you write actually works the first time, which is a huge, huge boost to productivity. So here's the really crucial takeaway. With Rust, you're not making that old sacrifice anymore. In fact, code written in Rust actually spends about 25% less time in the review process. So developers are moving faster. For what feels like the first time ever, the safest path is also the fastest path. The trade-off is broken. All right, so fixing the language is a massive step. But that's really only half the battle, right? We also need to think about the platform where the code runs. And that brings us to the other piece of this puzzle, another absolute game changer, WebAssembly. So WebAssembly, or WASM as everyone calls it, actually got its start in a kind of surprising place, your web browser. It was designed to run code in the browser safely, but it's turned into something so much bigger. Think of it now as this universal, super secure little box, a sandbox, that can run code written in pretty much any language on pretty much any device. We're talking from massive cloud servers all the way down to a tiny little sensor. Now, this super secure isolation, it's WASM's biggest superpower. But it also creates a brand new problem, right? If your code is completely locked away in this safe little sandbox, how in the world does it do anything useful? How does it say, read a file from your computer, or talk to another server over the network? Well, the answer is something called a system interface. It's the bridge to the outside world. The one you hear about most is WASI. It's creating a whole new standard, a really secure model based on capabilities. The catch is, you have to change your application to work with it. But there's another idea bubbling up with things like Wally. The goal here is different. Instead of making a new standard, it just tries to safely expose the features the operating system already has. That means you could take a complex existing app and get it running in WASM just by recompiling it. No big rewrite needed.
And the payoff for this approach, especially when it comes to speed, is just enormous. So a typical Docker container, it might take, say, half a second to start up. A WASM module using one of these thing interfaces, we're talking a couple of milliseconds. If you're running something like a serverless function that just needs to spin up, do one quick thing, and shut down, that difference isn't just big, it's absolutely monumental.
Okay, so let's put these two big ideas together. You've got the incredible safety of a language like Rust, baked in before you even run the code. Then you combine that with the super secure, portable runtime of WebAssembly. And when you do that, a whole new way of thinking starts to take shape. A philosophy that's not about adding more and more layers of complexity, but about stripping them away. It's about building highly specialized software by removing everything you don't need. And this whole philosophy, it leads us to this really cool concept called a unikernel. You can think of it as the ultimate in software minimalism. Instead of running your app on top of a big, clunky, general-purpose operating system, you take your application and you compile it with only the absolute bare minimum OS parts that it needs. The result is one single tiny self-contained file.
And you can really see the difference when you lay it all out. Look at VMs and containers. See all those layers between your app and the actual hardware? Unikernels just get rid of all of it. They strip it all away. What does that get you? Well, a tiny surface for attackers to target, crazy fast boot times, and in some cases, even a nice little performance bump, like 4% on heavy CPU tasks. This makes them perfect for those really specialized high-security jobs, like network gear or IoT devices, where every single millisecond and every bit of security matters.
So this really feels like a fundamental shift, doesn't it? We're moving away from these complex, do-everything, general-purpose layers and toward these minimal, highly specialized tools. It's completely reshaping how we think about building good software. Which leaves us with a final question to chew on. Maybe the future of code isn't about building bigger, more complicated systems. Maybe it's about building smaller, sharper, and much more focused ones.